Welcome to Get Your FRQ On. This question is from 2005. It is question 5, and it is not calculator active. In the question stem, we are given that a car is traveling, and we have a graph for the velocity of the car provided. In part A, we are asked to find the value of the definite integral from 0 to 24 of the velocity function v of t dt and explain its meaning with units. All right, so the integral would just be the area under the curve of the velocity. That function is a piecewise function. It's defined in terms of 3 line segments. The resulting graph is basically just a trapezoid. So we can find the area of that using just basic geometry formulas. The integral from 0 to 24 of v of t dt is going to be 1/2 the average, or the sum of the two bases, which is 24 and 12, times the height, which is 20, and when push comes to shove, that all comes out to 360. All right, now we also have to explain the meaning with units. So remember that when we have a function that describes the rate at which something occurs, the integral of that rate function typically means how much change has taken place. Well, if the velocity of the car is given by v of t, and that is in meters per second, then the integral from 0 to 24 should tell us how far the car traveled in that 24-second period. So, from time t equals 0 to time t equals 24, the car traveled 360 meters. Now, it's important to understand that when you have a question like this with a definite integral, you have to be specific about which 24-minute period you are referring to. So you would have to say something like, from time t equals 0 to time t equals 24, the car traveled 360 meters, or in the first 24 seconds, the car traveled 360 meters. If you just say something like the car traveled 360 meters over 24 seconds, or in 24 seconds, without specifying which 24-second period you're talking about, you put yourself at risk of not earning at least a point, because the amount that the car travels in any given 24-second period may not be 360 meters. What we do know for a fact is that it's 360 meters for this specific 24-second interval, so we have to specify that that is in fact the interval we are referring to. In part B of this question, we are asked to find v prime of 4 and v prime of 20, or state that they don't exist, or show that they don't exist, explain the meaning of those two values, and provide the correct units. All right, so the limit as t approaches 4 from the left of v prime of t is just the limit as t approaches 4 from the left of v of t minus v of 4 over t minus 4. That's just 5 if you do the math based on the graph. And the limit as t approaches 4 from the right of v prime of t would be the limit as t approaches 4 from the right of v of t minus v of 4 over t minus 4. That turns out to be 0. So we run into an issue here. This limit doesn't actually exist because the two one-sided limits, even though they exist, they do not agree. So we would conclude from this that v prime of 4 does not exist, since those two limits are not equal. Now I can do the same thing for t approaching 20, but I don't really need to. If you look at the graph for v of t, there's no corner or cusp at 20, so it's just part of a line segment. So if I want v prime of 20, I can just calculate the slope of that line segment, and I can do that using its endpoints. So the endpoints of that segment are 24, 0 and 16, 20. And if I plug that into the formula for slope, v prime of 20 is negative 5 over 2 meters per second per second. So v prime of 20 does exist, v prime of 4 does not. In part C, we are going to assume that a of t is the acceleration of the car, and then we are asked to find a piecewise function for a of t. All right, well, based on the graph of v of t provided, v of t is just 3 line segments, and a of t is the acceleration. Recall that the acceleration is the derivative of velocity. But our velocities are just given to us in terms of a piecewise function consisting of 3 line segments, so our acceleration should be constant over different intervals. So using the graph of v of t, a of t in a piecewise function would be 5 for all values of t between 0 and 4, 0 for values of t between 4 and 16, and negative 5 halves for values of t between 16 and 24. In part D, we are asked to find the average rate of change of the velocity function over the interval from 8 to 20. Then, we are asked to determine if there exists a c such that v prime of c is this average rate of change, or at least we're asked to determine if that c is guaranteed. Right, well, first we have to find the average rate of change of v over the interval from 8 to 20. So we can do that just by using a formula for average rate of change. That would be v of 20 minus v of 8 over 20 minus 8. Those values we can get from the graph. 10 minus 20 over 12, so negative 10 over 12 is negative 5/6. So the average rate of change of v over that interval is negative 5/6 meters per second per second. All right, so now we have to answer the question, is there a value of c guaranteed such that v prime of c is negative 5/6? Well, there would be such a c if v of t is differentiable over the entire interval from 8 to 20. If it is, we're all set. If it's differentiable over that interval, we can use the mean value theorem, and that would guarantee the value of c that we're interested in. But there's a problem. Our function a of t is v prime of t, and as we saw in the previous part, a of t is not defined at t equals 16, and since 16 is between 8 and 20, it's in the interval we are after. So a of t equals v prime of t doesn't exist at t equals 16, which means v is not differentiable at t equals 16, and that is inside the interval we're looking for, and so the mean value theorem does not apply. So, is there a value of c guaranteed? No. Now, there might still be one, but we can't guarantee that it exists because v is not differentiable at t equals 16. In order to guarantee the value of c, it would have to be differentiable on that entire interval. It isn't, so we can't guarantee it. All right, so the existence of a value of c such that v prime of c is negative 5/6 isn't guaranteed. Again, there might be one, but we can't guarantee it because the mean value theorem does not apply.